Now we're going to think about a simple model of interacting with another oscillator. So if you watched the metronomes synchronizing in the YouTube video, those metronomes were coupled with each other via a foam board, and so they were getting some kind of feedback from the phase of nearby metronomes. We're not going to look right now at interacting oscillators because that's a multi-dimensional problem, and we are currently only studying one-dimensional problems, so we can't have two oscillators that influence each other, but we can have a reference oscillator that influences the oscillator that we model. So imagine that there's a reference oscillator and it's just oscillating at some constant angular velocity. So we have this reference, and then we add our oscillator. And this is actually a model of a firefly. In some parts of the world, fireflies will respond to a light stimulus and will try to flash at the same frequency as a light stimulus. And so this firefly is trying to synchronize. And we're going to say that the frequency of the firefly is whatever its natural frequency is, plus some function that depends on both its own phase and the phase of the reference oscillator. And actually, specifically, it's going to be that its frequency is its baseline frequency plus some kind of catch-up frequency based on the phase difference between our oscillator and the reference oscillator. And so we want our oscillator to speed up if the reference oscillator is ahead, and we want our oscillator to slow down if the reference oscillator is behind. To make that more precise, we're going to speed up if the phase difference is between 0 and pi, so the reference is a bit ahead, and we're going to slow down if the phase difference is between negative pi and 0, so the phase difference is a bit behind. A function that does this very naturally is a sine of phi minus theta. And so this function is positive on 0 to pi, it's negative on negative pi to 0, and it's continuous. And so our very simple model of this oscillator that's being influenced by a reference is going to be that theta dot is equal to its natural frequency plus a times the sine of this phase difference. We want to ask the question, does something called entrainment occur? Entrainment is frequency matching of the firefly and the stimulus, even though they might have different natural frequencies. So in that case, the firefly is getting pulled along at the frequency of the stimulus. And so to answer that question, we'll study the phase difference, which we're going to call phi, between the reference and our firefly. So the equation for this difference is phi dot is equal to the angular velocity of the first minus the angular velocity of the second, and that works out to the difference of the two natural frequencies plus this a sine phi term. And actually, A is a dimensional quantity, and these two frequencies are also dimensional, and so we're going to non-dimensionalize this equation before analyzing it. To non-dimensionalize, we create a new time variable tau, and it's equal to our old time variable divided by some time scale, capital T. And so we substitute this in for time everywhere it appears. Note that the angular variable was already non-dimensional, so we actually only had one dimension in the whole equation. So that gives us d phi d tau times 1 over capital T is equal to our old equation. And we bring the capital T over to the other side. And now we have two dimensionless groups that appear. One is A times T, so both A and T are themselves dimensional, and mixed together they're dimensionless, thus it's a dimensionless group. And then T times the frequency of the reference oscillator minus the natural frequency of the firefly. These are the two-dimensionless groups, and we're going to set capital T. We're going to choose the value of this constant so as to get rid of one of these, specifically, I think this one. So we're setting a t to 1 by setting t equals 1 over a, and that results in this equation where now sine phi has no parameter in front of it, and the only parameter in our system is this difference in frequencies, difference in natural frequencies divided by a. So we're going to give that a parameter name. This is the parameter mu, and mu is proportional to the frequency difference between the two oscillators. So this is the equation that we're analyzing to understand the phase difference. When mu is between -1 and 1, we're subtracting sine phi, and so we get a picture that looks pretty much like this, where there are 2 points of intersection, and the first one is going to be stable, and the second one is going to be unstable. So there are 2 fixed points present for this range of the parameter. And then when mu is equal to 1, we're right at the saddle node bifurcation. There's exactly 1 fixed point. And when mu is greater than 1, there are no fixed points. Okay, well, what are the implications of this for our firefly? If there's a fixed point, then something called phase locking is happening, where phi is going to just reach some particular value, and so phi is going to be a constant, and so that means that phi is not necessarily 0, but it's simply a constant number. There's a constant phase difference between the first oscillator and the second oscillator, and that's what we mean by phase locking. They're moving at the same frequency, and their phase might not be identical, but whatever difference there is between it, it's a constant difference. And then once we no longer have a fixed point, we're in this situation of phase drift, where the relationship between the two oscillators is changing over time and is very much drifting. And so the range of entrainment is this range where there's a fixed point and we have phase locking. And so that's the range where -1 is less than or equal to mu is less than or equal to 1. And that corresponds to this kind of condition on the reference frequency. So if the reference frequency is within some band in relationship to the set frequency, we're going to have entrainment. And I want to note that this may be a pretty reasonable model for some species of fireflies, but there's actually a species of firefly that's even able to change its own angular velocity to help it better match a reference frequency. And if you were able to change both this little omega and this a, it would be even easier to be within this phase locking range. You'd be even more likely to have both oscillators going at the same frequency, but maybe out of phase.